Well, good day. We're talking today about Chapter 18, Planning of Tasks. And this chapter has a good number of interesting insights about how to plan for the overall PLC task, but it has some warnings as well having to do specifically with time and the issue of time. So we want to reflect on that a little bit, and we want to look at some examples from the past. And one was a song, and I probably, this dates me a little bit, but I remember this when it was a popular song. And it has to do with a guy that got on the MTA, which is in Boston, the Metropolitan Transit Authority. And he, for years, has only had 10 cents. Every day he got on, he paid a nickel, and he paid a nickel to get off. But they upped the entry fare to a dime, so he paid his entire 10 cents to get on, and he didn't have a nickel to get off. So he rode on the MTA forever, and he never was able to get off. So it's kind of a joke, but it's also a warning that you need to know what you're committing to before you get onto something. And this is a YouTube video if you want to listen to it. It's 1950s. Kingston Trio, if you're interested, but basically it's a warning to plan that you don't overextend yourself and then have to wonder what happened. And sometimes that's exactly what happens with a PLC, because they're a computer and they can have problems with timing and other issues, memory issues, timing issues. They all coordinate to make your life very miserable if you haven't given it enough space of time. Here's another example. I had this example from industry, and it's not a big example, but it shows you the idiosyncrasies that can sometimes pop up. I had a job that I was working on, and there was a high-speed pulsar card that was purchased, and it came in with these high-speed pulses, and they were to count the flow of liquid. But the flow, it was to be turned off by the main CPU. So there was a physical card that was counting pulses, but then that information was being reported over the backplane to the CPU, which made the judgment of when was enough. And the CPU was operating in a high enough speed, I'm guessing 10, 12, 15 milliseconds, that it could, if it was reading a good value, could turn off that flow and have the accuracy that was needed. But what actually happened was that the accuracy was really the flow that would have occurred about every 3/4 of a second, or about 0.75 seconds. And I was puzzled by the inaccuracy. I couldn't figure it out, and we wasted quite a few batches on that. And then I put a simple program in to look at the time between when the pulses being counted changed, and I looked at that time, and it was about 0.75 seconds. So the point was that this extra card that was doing this counting was not updating that count that often. It was updating it only about every 3/4 of a second, which was the time that we were reading it, and that was throwing us off. So ended up, I called the manufacturer of the card and said, why aren't you updating your number across the backplane more often than about every 3/4 of a second? And he said, oh, that's impossible. And I said, well, why don't you try it? And he did. He came back and said, you're right. And then we had to make a decision as to whether or not we were going to wait for them to figure it out, how to update that more quickly, or we're going to do it ourselves. And we did it ourselves. I actually took the pulse of the original count and took it through a little Red Lion counter that toggled every few counts. I think it was every 4 counts instead of every 2. But the original pulse was coming in, and I was able to divide that by 4, and then look at these pulses down here, and look at that output, and then that output was toggled on and off, and I could see this on my program controller. In other words, these changes were slower than the scan rate of the program controller, while these were faster than than that. So I was able to capture these pulses, and that was enough to be able to turn on and off the flow meter, to turn off and off the flow valve in order to let the right amount of fluid go into the batch. So this worked. The original concept didn't work, and it's just for one output, so we just went ahead and put that in and let it stand. So that was an eye-opener of sorts, that you can get caught up in this, and no, it's not your fault. It's the fault of the person that designed the original piece of equipment and didn't think that they needed to account for that. So it's just one of those things you can walk into, and it happens. So really, there's three types of tasks, and we talk about those a little bit through the whole course of this book, but here we talk about it, try to concentrate on it. There's continuous, periodic, and event-driven tasks. And continuous means it's just always going. That would be your OB1 in Siemens, your main program in Allen Bradley. These are your background tasks that are always running. They're not guaranteed to run on a clock, but they just run. Then you have periodic tasks that are guaranteed to run on a clock. And what kind of tasks are those? Those are some things that depend on an exact time difference to be able to run. And I'll point some of those out to you. But most of those are having to do with PID controllers, and the PID controller has to be able to calculate its algorithm on an exact basis, or as opposed to just whenever. So you can't have it being calculated maybe 30 milliseconds, and then maybe 50 milliseconds, and then maybe 100 milliseconds, because it depends on a strict regimen of when that execution occurs, that's how you set it up. And you can't tune a PID loop if you don't have that that regimentation, that strict clock execution. So you can't do it. So those have to be periodic. And then event-driven tasks are on an event. You really don't care about running this program except when a certain event occurs. And when that event occurs, you're going to run it, and then you're not going to run it again. So these are just a one and dones, but they are important, and you usually have to answer something that happens with them. So we go through some of these examples, and I'm going to let you go through them on your own. But we want you to understand that both Allen Bradley and Siemens treat this very importantly, and you have these three types of programming problems that you can that you can do. Okay. So we're going to talk just a little bit about the diagnostics of that, and we're going to look at interrupt latency. If something happens that you don't think is supposed to happen, or it happens in a non-timely manner. So it is explained in this chapter a little bit about things that can happen, like an error, and that something exceeds a maximum time, or that type of thing, or an OB cannot be started, or it started and ran and then ran out of time and couldn't happen again. And these are all timing error events. Those are things that can either happen that the PLC reports back to you and shuts you down, or that you have something that can shut down your process. So those are all faults that can occur either through the program controller or through your programming. So here is a trace of a type of problem or program that was run by Siemens. And these are good. These are good to be able to look at and diagnose. And also I wanted to look at an example of a timed interrupt program that was necessary to look at the number of calories that are being with the bike that happen. So you have to run the bike program based on a timed program, and that timed program is every so often on the in your calculations. So basically, the pulses are coming in, and there's okay. So this is the one with the calorie program, and this other program then is talking about the speed of the number of pulses that are being received. So when you have an encoder that is recording back a speed indication, there were only at 100 in 10 milliseconds pickup, you could only get one part in 12. In other words, you could only at the maximum speed get only 12 pulses. So you need a more high accuracy than 1 in 12. So you have to slow down your program to capture more pulses. So if you go down to 100 milliseconds per time period, you can get 120 pulses, which is much more. One part in 120 is you can have more accuracy. So you don't want something operating on a 1 in 12. You want it operating on a part in 1 in 120, because if it changes by 1 in 120, that's not much of a change. If it changes one part in 1 in 12, that's a huge change. So you don't want to have to do that. But your accuracy now is over 100 milliseconds as opposed to 10 milliseconds, which is not good because you can't change very quickly. So that is a compromise that you must make if you're going to design systems. You have to be able to get enough pulses to operate over the time period that you want to be able to accurately predict over. So in other words, you got to go buy a more expensive encoder than the ones that we've been buying on these simple applications. Here is the case of how these are being read in, and I want to show you how this program is actually set up for reading in these pulses. Here, you're reading in the pulse, and then you're looking at saving the difference between this time and last time, and then you're saving this times into the last time. So basically, you're getting the input of how many that happened this time in here. So this is a scrolling number, just keeps getting bigger and bigger and bigger and bigger and bigger in your number. So at each time you come in and read, you say, well, how many occurred since the last time? And you subtract new versus old, this versus last time here, and that's where the subtraction occurs. And then this is the new input pulse number, and then you save the new number into the old number, and that's how you do that. Okay, so here is another problem that is a textbook problem. You can do it if you want to. It has to do with boxes. Their flow is from left to right, and there's a knife that comes up and that shuts you down if you want to. But basically, these boxes are flowing up, and they hit this photo eye, and you've got a high-speed pulse counter that's saying how fast the speed is, and it says basically that if the trailing edge of the prior box is not far enough away, in other words, it hasn't moved enough, I want to hold that box back so that I have an even distance between my boxes. Now, if the photo eye says that if the photo eye sees it and there's already that amount, it just says, okay, keep on going. In other words, if the distance from here to here is greater than the distance from here to here, just let it rip, just let it go, don't bring the knife up. But if the distance isn't that much, if it's little like this, I want to at least spread them out to this amount. So this program is based on looking at pulses on an interrupt-driven basis, on a timed interrupt basis, and saying how many have traveled for so, and then basically putting this knife up only if your spacing is less than this minimum spacing. So that's a problem you can work on. And here's another anecdotal. So this is what I ran into when I first started my engineering career. This is a bigger one. This is a heavy-duty problem, and that was because we had a cutting machine that was the the control of all the glass on a major glass manufacturer's control line that came out of the furnace had to be controlled and moved onto these various side legs and sidelines. So if you can picture a big conveyor system coming down, roll conveyor with pieces of glass coming down, and then having to go off of on the side to be transferred to side legs so that they could be picked off or cut up again and then picked up that way. So I had 66 sections of conveyor, and the original one that had been done before that had 7 sections really of conveyor. And I noticed that the interrupt program that had been driven for that one was very intense. In other words, the light that was showing for that level of activity was very bright. And I had 10 times that number of inputs. Now, each of the inputs was represented a travel of 1.5 inches of travel of that conveyor. So each 1.5 inch of travel, I'd get another interrupt. That was the plan. Well, the guy that had done that, he quit, and he left me to basically write this program myself. And so I looked at it, and I looked at that light, and I said, I'm going to 10 times that number of inputs per unit of time. And that light is pretty heavy on right now. So I really don't know if I'm going to run out of time or not. So what I did was I wrote it on one interrupt, one cyclical interrupt of 8 milliseconds. And I asked the question each 8 milliseconds, is it the same as it was last time, 8 milliseconds ago? And if it was, I left it alone. If it wasn't, I went and incremented, instead of 1.5 inches, I incremented 0.75 inches. So I was saying I'm going to be twice as accurate because I'm going to be able to do something every 0.75 inches as opposed to 1.5 inches. But I'm going to do it on one interrupt instead of 66 interrupts. And because interrupts take time to service, this worked out very, 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 very well. One interrupt instead of 66, and it worked. And the light on the program that I did was less intense than the light on the program that was running with the 6 sections of conveyor. Now, it may just been the light bulbs were different styles or whatever, but it worked, and it worked much, much, much better. And it was more accurate. It had better accuracy than the other one. And the other side of that coin was that this is my first big programming project, and I had never done anything with this kind of thing before. And I just decided to do it. After I had made that change, there was a discussion one day around the water fountain about something or another. And my boss was there and I was there, and I just made the statement, well, I changed that. And that part of the program, and that was the part of the program that he was talking about. And he had no real indication of what would happen if it didn't work or did work or whatever, but I was responsible for it. So I said to him, I just said it over the group of people that were there, well, I changed that to a cyclical program. And I thought maybe I was going to get fired after that. I didn't know what was going to happen, but we had to go through a review. And after the review, he said, well, that's okay. Let's just go ahead with what you've done. So it worked, and it worked better. And I came to the conclusion after that it is better to ask for forgiveness than ask for permission. I doubt if my boss would have gone along with the theory that the program would have fallen apart because the other guy had been the expert. But I don't believe it would. I don't think that it would. I think it would probably would have fallen apart. And in the process of doing that, we showed that the computer that we had bought at that time, which cost $100,000, could have easily been replaced by another computer that was in the $30,000 range, a saving of $70,000, which was much, much, much more than my salary ever was in that era. So it was a good move. It was one of those moves that did help, and I'm glad that I did it, but it was not without difficulty. Okay, so here is a listing of the sum of the instruction times and how long they take, and that is something that you might be interested in. Also, we have added to this chapter some of the updates from the Siemens Programming Guide version 16 that was published back in after version 14, excuse me, back in 2018. So these are updates, and I'm just going to go through them rather quickly. But they're updates from the how the Siemens software has been updated and some of the things that have been done in the later versions. And I'm just going to go through them rather quickly, but this is a big part of this chapter, and some of them are worth commenting on. Okay. So I have not done this, but this is something that you might end up doing, of optimization of machine code. And in writing your code, you've written almost all of them if you're a Siemens in OB1. And that's probably not the best place to write large programs. The best place probably is in FBs and their accompanying OBs. And if that's the case, then you can optimize these blocks. So these blocks can be optimized, and this is the steps that you can use to do that. So you actually are going to be asking, what do I have to do in order to do this? I want to optimize the structure of those blocks. What does this do for you? Well, it makes the program run faster. So if you don't care, don't do this. But if at some point in time you run out of time, do this. Simple. So you might do it anyway, just to make sure that you've got your that you optimize the speed of your program. If you write in the FB OB mode, and that's probably where you're going to end up doing most of your writing if you're a Siemens programmer, this is going to happen. You're going to do this optimization, and you're going to do it probably on a daily basis. Or you're out at lunch or something like that, you're going to let this happen. Okay. And here's a little bit about optimized blocks. Conversion. So here are some of the types of blocks, and we've seen some of this, but some of these are the old 300 and 400 and now the 1200 and 1500, some comparison between them that you haven't seen before. Those have been increased. This is where they're increased. And also, to be able to have parameters that you can show and hide, you can create this tab down at the bottom. And they've also brought in 64-bit data. Instead of 32-bit as a long, now they go to 64-bit. So you can have really big numbers and really, really, really accurate numbers as opposed to not quite as accurate numbers. And also a 64-bit time data block. So that is included. And also Unicode, which gives you the capability of communicating in Chinese if you want to. The variant data type I have not used, but here's some instructions on it. If you want to, you can try this. You're welcome. The variant data type is described here, and some of its attributes, and some of the things you can do with it. How you put it into an array of variant type, for instance. Okay. What's the advantages of variant type? Here are some of the advantages. The runtime instruction tells you how long each of these blocks are running. And the idea of libraries, again, this has something to do with chapter 14, but it lends itself to being able to store large amounts of programs in these libraries and be able to reuse them. It talks about some of the places where that you can find these libraries at, and you can reuse those, or you can create your own type of libraries and library elements. Again, bigger projects would use these, and you would probably be using these in those types of projects. These are how to do that. Describes how to do that. So this is describing the differences between the typifiable objects for controllers and HMI. And it gives you some of that information with types. Again, I've not used this before, but you're certainly welcome to read through this and this information. I brought it into my area, but it's either available there or in the Siemens texts. It's impossible to keep up with all the things that have changed in these controllers, so this is an example of something that I thought was important that I would bring in. Maybe something that you'd be interested in. So here's a way of increased performance for hardware interrupts. Again, if you run into this problem, here's something that you might be interested in doing. On a 1500. And here are some tips and tricks in the SCL language. If you're trying to bring down programming in SCL, here's some of the things that you might be interested in doing. So again, I'm not going to bore you with my interpretation of these because you can read through them, but again, they're there for a reason, so we want you to understand these concepts. Here's the good way of making an if statement. And it's important to use hardware-dependent functions, not to use hardware-dependent functions, but use hardware-independent functions. So as you go through these, you may want to study some of these, but if you're going to try to move from processor to processor, and you will, you're going to probably look at which ones of the instructions are dependent on that particular processor and which are not. And so again, probably for timer and counter would be the ones that you probably would be concentrating on. So This chapter is a lot of do's and don'ts, but also it's a chapter just of a warning that you are responsible for keeping track of the amount of time and the amount of memory that you're using, and use it in a responsible way so that you don't run out. And that's why the Charlie and the MTA, and that's why all the other examples. It's just a warning. This is a chapter of just being careful and proceeding at a cautious pace. Also, one of warning you that you're going to have to split your process up into multiple processors, and that's up to you how you make those decisions. That's why they pay you to make those kind of decisions. So, wish you the best. And this is a good chapter. You may not think too much about this chapter, but you will when you get to actually implementing code real world. Thanks. Have a good day.